Roughly 252 million years ago, the Permian Ocean was one of the most biologically elaborate systems Earth had ever produced. It was not a simple sea. It was the accumulated result of nearly 300 million years of continuous marine evolution. Layered, interconnected, and operating across every depth zone from sunlit surface waters to the cold, pressurized seafloor. Coral-like organisms called rugose and tabulate corals had constructed vast reef structures along shallow continental margins, some extending for hundreds of kilometers. These were not merely geological formations. They were biological architectures, frameworks of calcium carbonate secreted over millions of years by colonial organisms, riddled with chambers and surfaces that supported extraordinary concentrations of associated life. Brachiopods carpeted the seafloor in densities that may have reached hundreds of individuals per square meter in optimal habitats. Sea lilies extended their feeding arms into slow currents, processing microscopic organic material drifting down from above. Bryozoans formed delicate colonies across hard substrates, filtering plankton from water that moved steadily through the system. Ammonoids, free-swimming cephalopods with elaborately chambered shells, ranged from small palm-sized individuals to larger forms approaching half a meter in diameter, navigating the water column by adjusting the gas-to-liquid ratio within their internal chambers. An estimated 90 to 95% of all marine species then in existence were distributed across these interconnected ecological roles, each shaped over millions of generations to exploit a specific resource or occupy a specific space. Before we continue, take a moment to consider where you're watching from, which country, and how far removed it is from an ancient world where the oceans themselves became a threat, spreading conditions that pushed life toward one of its greatest crises. If these journeys through Earth's deep past hold your attention, consider subscribing to continue exploring them. It's always remarkable to see how far these stories travel. Dim the lights, settle into the quiet, and let the modern world fade as dark waters spread across ancient seas, carrying unseen changes through a planet slowly drifting toward catastrophe. At the upper levels of this system, apex predators moved through water that was clear, oxygen-rich, and biologically dense. Among the most formidable were large cartilaginous fish belonging to lineages that had been refining their predatory architecture for over 100 million years. Some had reached lengths of 6 to 8 meters, with dentition arranged in spiral whorls along the lower jaw, structures capable of seizing and processing prey of substantial size. Alongside them, large-bodied bony fish had diversified extensively across different depth zones and feeding strategies. Some were filter feeders exploiting the dense planktonic productivity of surface waters. Others were active pursuit predators, anatomically adapted for speed and maneuverability. The presence of multiple large-bodied predator types within the same system indicates a food web of sufficient productivity to support energy demands at the highest trophic levels. The ocean in this period functioned as a three-dimensional hunting ground of enormous extent, approximately 335 million cubic kilometers of water, most of it habitable, most of it occupied. The system was not fragile in any obvious sense. It had survived ice ages, sea level fluctuations, and gradual climatic shifts across hundreds of millions of years. What it could not survive was a change in ocean chemistry that operated faster. Evolution could respond. The first indicators of systemic stress were not sudden. Ocean temperatures began to rise, driven primarily by the massive volcanic outgassing of the Siberian Traps, a flood basalt province releasing carbon dioxide and sulfur compounds at a sustained rate over tens of thousands of years. Evidence preserved in oxygen isotope ratios within marine fossils and carbonate sediments indicates that sea surface temperatures increased by an estimated 8 to 10 degrees Celsius across the extinction interval. For marine organisms, temperature is not simply a comfort variable. It governs metabolic rates, reproductive cycles, and, critically, the solubility of oxygen in seawater. Warmer water holds less dissolved gas, At 30 degrees Celsius, seawater holds approximately 40% less dissolved oxygen than it does at 15 degrees Celsius. For organisms that had evolved over millions of years in cooler, oxygen-rich conditions, this represented a fundamental shift in the chemical environment they depended upon. Simultaneously, the absorption of excess atmospheric carbon dioxide was altering the ocean's carbonate chemistry. Dissolved carbon dioxide reacts with seawater to produce carbonic acid, which reduces the concentration of carbonate ions. The very ions that reef-building organisms use to construct their calcium carbonate skeletons and shells. This process does not dissolve existing structures immediately. It works more slowly, reducing the rate at which organisms can calcify, weakening shells and reef frameworks over time, and eventually crossing thresholds below which calcification becomes energetically impossible. Evidence from Permian carbonate sediment records suggests that ocean pH declined measurably across the extinction interval, with estimates ranging from 0.1 to 0.7 pH units depending on the geological proxy used. These changes did not affect all regions uniformly. The ocean is stratified, layered by temperature and density, and this stratification controls the circulation of oxygen from surface waters downward into the ocean interior. Under normal conditions, cold, dense surface water sinks at high latitudes and carries dissolved oxygen into the deep, maintaining aerobic conditions throughout most of the water column. As surface temperatures rose, and the temperature contrast between tropical and polar waters diminished, this circulation began to slow. The density difference driving vertical mixing decreased, and oxygenated surface water no longer reached intermediate and deep layers at the rate required to sustain the organisms living there. Current models suggest this deoxygenation accelerated substantially during the peak volcanic activity of the Siberian traps, which is estimated to have released between 40,000 and 100 gigatons of carbon into the atmosphere across the extinction interval. In the deeper parts of the ocean, where oxygen replenishment depends entirely on vertical circulation, conditions began shifting toward hypoxia, concentrations too low to support most animal life. This was not immediately visible at the surface. The upper ocean, still in contact with the atmosphere and still productive, retained oxygen and continued to support marine communities. But beneath that functioning surface layer, the ocean was quietly changing. Dead zones were expanding upward from the seafloor. The habitable volume of the sea was contracting. Organisms that had occupied the deep and intermediate water column for millions of years were encountering chemical conditions their physiology had no capacity to tolerate. The reef system showed early signs of stress in the form of reduced calcification rates and declining skeletal density, changes detectable in the fossil record as a gradual thinning and simplification of reef structure before outright collapse. Filter feeders on the sea floor experienced disruption in the flow of organic material from above, as the planktonic community sustaining that flux began to respond to altered surface, chemistry, and temperature. Predators at the upper levels of the food web continued to hunt, but the prey density beneath them was beginning, almost imperceptibly, to thin. What was unfolding was not a single event with a clear beginning and end. It was a cascade, a sequence of interdependent changes in temperature, oxygen, and ocean chemistry, each one compounding the stress produced by the others, advancing across tens of thousands of years toward a threshold from which the ocean would not quickly recover. The sea that had supported life in extraordinary abundance for hundreds of millions of years was, by measurable degrees, beginning to turn against it. The apex predators of the Permian Ocean had not evolved for a world in crisis. They had evolved for abundance, for deep, oxygen-rich water, for dense prey populations distributed across a wide and navigable water column, for a biological system producing enough energy at every trophic level to sustain animals of considerable size and metabolic demand. As ocean temperatures climbed and dissolved oxygen concentrations began their long decline, these animals were among the first to register the consequences, not because they were the most chemically sensitive, but because they operated at the highest energetic cost. Large-bodied predatory fish require disproportionately more oxygen per unit of body mass than smaller organisms. Sustained pursuit, the fundamental mechanism of open water predation, depends on aerobic metabolism, which depends directly on oxygen availability in the surrounding water. As hypoxic conditions expanded through intermediate water layers, the vertical range within which large predators could effectively hunt began to compress. Animals that had previously ranged freely across hundreds of meters of water column were increasingly constrained to shallower depths where oxygen concentrations remained marginally sufficient. The hunting ground was shrinking, and the predators within it were being forced into closer proximity with one another and with their prey. Among the most well-documented large predators of the late Permian seas were the edestids and related eugenodont sharks, cartilaginous fish with a fossil record extending back into the Carboniferous. By the Permian, some lineages had reached lengths estimated between 6 and 10 meters, with the distinctive tooth whorl structure of the lower jaw representing one of the more unusual predatory adaptations in vertebrate history. The precise function of this structure remains debated, but current hypotheses suggest it was effective for seizing soft-bodied or scaled prey, with the spiral arrangement of teeth allowing successive rows to engage as outer teeth wore or were shed. These animals were not opportunistic scavengers. Their anatomy indicates active, pursuit-based predation in open water, a strategy that became increasingly costly as oxygen availability declined. Cephalopods occupied a different but equally significant position in the Permian predator community. The ammonoids, already diverse and widely distributed across the water column, included forms that were themselves active predators of smaller fish and invertebrates. Nautiloid cephalopods, relatives of the modern nautilus, though far more varied in the Permian than their single surviving descendant today, used jet propulsion and grasping tentacles to capture prey in both shallow and deeper water environments. Unlike the large cartilaginous fish, cephalopods have relatively lower metabolic rates and tolerate moderate reductions in oxygen concentration more effectively. This physiological difference would prove significant. As conditions deteriorated, cephalopods demonstrated a measurable persistence in the fossil record that larger, more metabolically demanding vertebrate predators did not. The behavioral consequences of a shrinking oxygenated zone are reconstructible through analogy with modern systems. In present-day oxygen minimum zones, regions of the ocean where dissolved oxygen drops below approximately 2 milliliters per liter, large fish are excluded almost entirely, while smaller organisms with lower oxygen demands persist at the boundaries. Predator-prey interactions concentrate at these boundaries, creating temporary zones of intense biological activity at the edges of habitable water. Evidence suggests that analogous compression effects operated during the Permian oxygen decline, forcing predators and prey into shallower, warmer surface layers already under thermal and chemical stress. This compression did not simply intensify competition, it disrupted the spatial architecture of predation itself. Many prey species had evolved escape strategies dependent on vertical movement, diving into deeper, darker water to evade surface predators. As the oxygen-depleted layer expanded upward, this escape route closed. Prey animals were increasingly confined to the same narrow band of water as their predators, with nowhere to retreat. The result, inferred from patterns in the fossil record showing rapid turnover and size reduction among prey species during this interval, was an acceleration of predation pressure at precisely the moment when prey populations were already under physiological stress from warming and acidification. The large fish themselves were not responding to these pressures with any form of behavioral adaptation in the evolutionary sense. The timescale was far too compressed for natural selection to produce meaningful anatomical or physiological change. What the fossil record shows instead is a pattern of range contraction, body size reduction in some lineages, and ultimately disappearance from regions where environmental conditions crossed critical thresholds. Genera that had been distributed across broad oceanic regions in earlier Permian strata become progressively restricted in their geographic occurrence in sediments closer to the extinction boundary, before vanishing entirely. The giant cephalopods showed a more complex trajectory. Some ammonoid lineages contracted sharply in diversity during the early phases of environmental deterioration, then stabilized, then contracted again as conditions worsened. This pattern of partial recovery followed by renewed decline is consistent with organisms responding to an environmental stress that was not continuous but episodic, punctuated by periods of relative stability between pulses of volcanic activity from the Siberian traps. The ocean was not dying at a constant rate. It was deteriorating in stages, each pulse of warming and deoxygenation pushing marine communities closer to thresholds from which recovery became progressively less complete. What these animals experienced, translated into measurable environmental terms, was a water column that was simultaneously warmer, more acidic, lower in dissolved oxygen, and increasingly stratified, meaning that the vertical mixing required to replenish oxygen in deeper layers was occurring more slowly than the biological demand for that oxygen was consuming it. The chemical trajectory of the ocean was not yet at its most extreme. That would come later, as deeper processes already in motion beneath the seafloor continued to develop. But the predators of the Permian surface ocean were already operating in a world that was measurably less capable of sustaining them than the one their anatomy had been shaped to inhabit. The hunting continued, the seas still moved, but the margin between function and failure was narrowing with each degree of warming, with each fractional decline in the oxygen that made large, fast, metabolically expensive life possible. Beneath the hunting grounds of the surface ocean, the seafloor of the late Permian was undergoing a transformation that produced no immediate visible signal at the surface but would ultimately determine the fate of the entire marine system. The deep ocean was losing oxygen, not gradually in the way that a slow leak might be described, but systematically in expanding regions that grew larger and merged over time, converting habitable seafloor into zones where aerobic life could no longer persist. The mechanism driving transformation was the same one reshaping the upper ocean, but its consequences at depth were more absolute. In a well-circulating ocean, cold, oxygenated water sinks from the surface at high latitudes and travels along the seafloor, replenishing oxygen consumed by the respiration of bottom-dwelling organisms and the bacterial decomposition of organic material raining down from above. This process, thermohaline circulation, is sensitive to temperature gradients. As the Permian climate warmed and the temperature difference between equatorial and polar surface waters diminished, the density contrast that drives this deep circulation weakened. The sinking of oxygenated water slowed. In some regions, current models suggest it may have effectively ceased. The consequences for the seafloor were not immediate but were cumulative and self-reinforcing. As oxygen delivery declined, the bacterial communities responsible for decomposing organic material shifted from aerobic decomposition, which consumes oxygen, to anaerobic pathways which do not require it. These anaerobic bacteria produce different chemical byproducts. Among the most significant is hydrogen sulfide, a molecule toxic to most aerobic organisms at concentrations above approximately 2 micromoles per liter. In anoxic sediments, hydrogen sulfide is produced continuously as sulfate-reducing bacteria process organic carbon using dissolved sulfate as an electron acceptor instead of oxygen. Under normal oceanic conditions, this hydrogen sulfide remains confined to sediment-poor waters, oxidized before it can accumulate in the overlying water column. But in an ocean where oxygen delivery to the deep has slowed substantially, this containment mechanism begins to fail. The seafloor environments that developed under these conditions were unlike anything that had existed across the preceding hundreds of millions of years of complex marine life. Sediment cores and geochemical proxies from late Permian and earliest Triassic deposits reveal the presence of biomarkers, molecular fossils, specific pigmented bacteria that can only exist in water columns where hydrogen sulfide sunlight overlap. These organisms, known as green sulfur bacteria, conduct photosynthesis using hydrogen sulfide rather than water. Their presence in the geological record is a reliable indicator that oceanic conditions, anoxic and sulfide-rich water, extended upward from the seafloor into the photic zone, the upper layer of the ocean reached by sunlight. This is not a marginal or localized signal. Evidence of these conditions has been recovered from Permian-Triassic boundary sediments across multiple paleocontinental regions, suggesting that Oceania was geographically extensive rather than restricted to isolated basins. For the organisms that had inhabited the seafloor across the Permian, this chemical transformation was lethal without exception. The benthic communities, the brachiopods, echinoderms, bryozoans, and worms that had carpeted the ocean floor in extraordinary diversity, had no physiological mechanism to tolerate hydrogen sulfide at the concentrations developing in these expanding dead zones. Their response, preserved in the sedimentary record with striking clarity, was disappearance. In stratigraphic sections from the Permian-Triassic boundary, the rich and diverse assemblages of benthic fossils, characteristic of the mid and late Permian, give way abruptly to sediment layers that are largely or entirely barren of skeletal remains. These barren layers are frequently laminated, thin, undisturbed horizontal bands indicating the complete absence of bioturbation, the physical mixing of sediment by burrowing organisms. When burrowing organisms are absent, sediment accumulates in undisturbed layers. The lamination is itself a fossil, a record of biological absence. The expansion of these anoxic and oceanic zones did not proceed uniformly across the seafloor. Deeper basins, where water circulation was already reduced and organic material accumulated in greater quantities, crossed into anoxia first. Shallower shelf environments, the broad, relatively flat regions of seafloor extending from continental margins to depths of approximately 200 meters, were initially more resilient, maintained by proximity to oxygenated surface waters and the continued, if diminished, mixing of the upper water column. But as warming progressed and stratification intensified, even these shallower regions began to experience seasonal or episodic hypoxia that grew in duration and severity over time. The seafloor was not simply emptying, it was being chemically replaced. In regions where aerobic life had been eliminated, novel microbial ecosystems dominated by anaerobic bacteria and archaea expanded across the sediment surface. These communities processed organic material through fermentation, sulfate reduction, and methanogenesis, metabolic pathways that produce methane, hydrogen sulfide, and carbon dioxide as byproducts, each of which fed back into the broader chemical transformation of the ocean. Methane escaping from seafloor sediments contributed additional greenhouse, forcing to an atmosphere already loaded with volcanic carbon dioxide. Hydrogen sulfide accumulating in bottom waters began diffusing upward into intermediate depths. The chemistry of the deep ocean was not passively responding to surface conditions. It had become an active contributor to its own deterioration and to the deterioration of the layers above it. What the late Permian seafloor represented in physical terms was a system crossing from one stable chemical state into another. The aerobic ocean, the ocean that had sustained complex animal life for hundreds of millions of years, was being displaced from below by an anaerobic ocean governed by different chemistry, different microbiology, and fundamentally different rules about which forms of life could persist. The transition was not yet complete. But across the deep seafloor of the late Permian, vast regions had already crossed that threshold, and the boundary between the habitable and the uninhabitable was moving steadily upward toward the light. The reefs of the late Permian Ocean were among the most structurally complex ecosystems the bare planet had yet produced. They rose from shallow continental shelves in formations that extended for hundreds of kilometers along coastlines that have since been fragmented and redistributed across the globe by plate tectonics. Built primarily by calcareous sponges, calcified microbes, and bryozoans. The tabulate and rugose corals that had dominated earlier reef systems having declined significantly by the late Permian. These structures were not static formations. They were living systems, constantly growing, eroding, and rebuilding, maintained by the collective biological activity of thousands of interdependent species operating across every surface and crevice of the reef framework. The productivity concentrated within these reef systems was disproportionate to the area they occupied. Though shallow reef environments represented a relatively small fraction of total ocean floor, they supported a density of species and ecological interactions that far exceeded anything found in the open ocean or across the flat, sediment-covered abyssal plains. Fish moved through reef structures in complex patterns governed by feeding territories, predator avoidance, and spawning behavior. Invertebrates occupied every available substrate, boring into the carbonate framework, encrusting exposed surfaces, filtering water from within sheltered crevices. Predators ranging from small reef-associated fish to larger pelagic hunters moved in and out of the reef environment, exploiting the concentrated prey that reef complexity generated and sustained. The ecological relationships within these communities had been refined across millions of years of coevolution. Cleaning behaviors, where smaller organisms removed parasites from larger ones, were likely already established in some form. Predator-prey relationships between reef fish and invertebrates had produced elaborate morphological adaptations on both sides. Hardened shells, cryptic coloration, spines, and chemical deterrents on one side. Specialized dentition, sensory refinement, and behavioral flexibility on the other. The reef was not simply a habitat. It was an evolutionary arena that had been operating continuously long enough to produce layers of biological complexity that are, in retrospect, almost impossible to fully reconstruct from the fossil record alone. The first measurable impacts of ocean warming and acidification on these systems appeared not as sudden structural collapse, but as a progressive, physiological impairment of the organisms responsible for building and maintaining the reef framework. Calcification, the biological process by which organisms extract calcium and carbonate ions from seawater to construct skeletal material, is energetically demanding under optimal conditions. As ocean pH declined and carbonate ion concentrations fell, the energetic cost of calcification increased while the availability of the necessary ions decreased. For reef-building organisms already allocating significant metabolic energy to growth and reproduction, this represented a compounding stress that manifested first as reduced growth rates and thinner skeletal structures, and later as an inability to calcify at rates sufficient to offset natural erosion. Geochemical analysis of carbonate sediments from Permian-Triassic boundary sections reveals a measurable decline in the isotopic signatures associated with robust biological calcification in the interval preceding the extinction boundary. Reef frameworks show evidence of increased microbial encrustation relative to Metazoan skeletal contribution, a pattern consistent with the selective elimination of calcifying animals and the persistence of microbial mat communities that require no mineralized skeleton. This shift from animal-dominated to microbe-dominated reef surfaces is one of the clearest early signals of ecological collapse preserved in the rock record, visible in outcrops from what were once reef environments across the ancient Tethys Sea and the margins of Pangaea. The fish and mobile invertebrates associated with reef environments responded to structural degradation and water quality decline in ways that the sedimentary record captures only partially. Species diversity in reef-associated faunal assemblages decreases measurably in fossil collections from sediments approaching the Permian-Triassic boundary, with the loss concentrated among specialists. Organisms with narrow ecological requirements dependent on the structural complexity and chemical stability of intact reef environments. Generalists, organisms capable of exploiting a wider range of conditions and food sources, persisted longer. This pattern of specialist loss preceding generalist loss is consistent with ecological theory, predicting that habitat simplification eliminates ecological niches before it eliminates the organisms capable of occupying multiple niches simultaneously. Predator-prey dynamics within reef communities were disrupted in ways that compounded the structural deterioration of the reef itself. Many reef-associated predators depended on the physical complexity of the reef framework, its channels, overhangs, and sheltered zones, to ambush prey or pursue them through confined spaces. As the reef framework thinned and simplified, these behavioral strategies became less effective. Prey species lost the structural refuges that reef complexity had provided. Predation pressure, concentrated into a simplified and shrinking habitat, accelerated the decline of prey populations already stressed by thermal and chemical conditions. The biological community of the reef was not simply responding to an external stressor, it was participating in a feedback process in which ecological disruption accelerated physical deterioration, and physical deterioration deepened ecological disruption. Thermal stress added a direct physiological dimension to the chemical pressures already affecting reef communities. Many reef-associated invertebrates have narrow temperature tolerances, and the 8 to 10 degree Celsius warming, estimated across the extinction interval, significantly exceeded the adaptive range of organisms evolved in the relatively stable thermal conditions of the mid-Permian Ocean. At temperatures above their physiological tolerance thresholds, marine invertebrates experience impaired reproduction, reduced immune function, and disrupted larval development. For reef communities dependent on successful larval recruitment to maintain population sizes, thermal stress at this level represented a threat to the long-term viability of populations even before mortality from direct exposure became a factor. What the late Permian reef systems represent in the fossil record is a portrait of biological complexity at the precise moment before its dissolution. The rock sections that preserve these environments record, in their stratigraphy, the transition from diverse and structurally elaborate reef communities to impoverished microbial assemblages within intervals that, geologically speaking, are extraordinarily brief. The reefs did not fade slowly into the background of Earth history. They stood, biologically dense and ecologically intricate, until the compounding pressures of temperature, acidification, and deoxygenation crossed thresholds that their constituent organisms had no capacity to withstand. And then, layer by layer in the sedimentary record, they went silent. Oxygen is not simply one variable among many in the chemistry of the ocean. It is the foundational condition upon which the entire architecture of complex marine life depends. Every animal in the Permian Sea, from the smallest brachiopod filtering particles from the water column to the largest cartilaginous predator, patrolling open water, required a continuous supply of dissolved oxygen to sustain cellular respiration. Remove it, or reduce it below critical thresholds, and the biological machinery of animal life begins to fail in ways that are rapid, irreversible, and cascading across every level of the food web simultaneously. By the late Permian, the ocean's capacity to distribute oxygen through its interior was failing in measurable and accelerating ways. The thermohaline circulation that had historically delivered oxygenated surface water to intermediate and deep layers was operating at a fraction of its former efficiency, suppressed by the reduction in surface temperature gradients driven by sustained greenhouse warming. Stratification, the tendency of warmer, less dense surface water to remain separated from cooler, denser water below, was intensifying across large areas of the global ocean. The vertical mixing that oxygen delivery depends upon was being physically inhibited by the same thermal forcing that was simultaneously reducing the amount of oxygen that surface water could hold. The result was a contracting envelope of habitable water. Oxygen minimum zones, regions of naturally reduced oxygen concentration that exist in the modern ocean at intermediate depths, typically between 200 and 1,000 meters. Due to the respiratory demand of microbial communities, decomposing sinking organic material expanded dramatically in both vertical extent and geographic coverage. In the modern ocean, these zones occupy roughly 8% of the total ocean volume. Geochemical proxies from Permian-Triassic boundary sediments, including the isotopic composition of nitrogen, iron speciation data, and the distribution of redox-sensitive trace metals such as molybdenum and uranium, indicate that anoxic and severely oxygen-depleted water masses occupied a substantially larger fraction of the late Permian Ocean, with some reconstructions suggesting that oxygen-deficient water extended into the photic zone across significant portions of the Tethys Sea and adjacent in-ocean basins. For the marine organisms still persisting in shallower, better oxygenated waters, this expanding oxygen depletion created a vertical compression effect with direct ecological consequences. Animals that had previously distributed themselves across a wide depth range were forced upward into an increasingly narrow surface layer. This compression increased local population densities in the remaining habitable zone, intensifying competition for food, space, and the oxygen itself. Organisms with higher metabolic oxygen demands, larger animals, active swimmers, organisms with high reproductive investment, were selectively disadvantaged relative to smaller, less active forms capable of sustaining function at lower oxygen concentrations. The physiological responses of marine animals to declining oxygen are well characterized from both experimental biology and observations of modern, low-oxygen environments. At oxygen concentrations below approximately 4-6 milligrams per liter, a threshold commonly used to define hypoxia in marine systems, many fish species begin to exhibit impaired swimming, performance, reduced reproductive output, and behavioral changes, including avoidance of deeper water and congregation near the surface. Below approximately 2 milligrams per liter, most fish cannot sustain aerobic metabolism and begin to experience cellular damage. Invertebrates vary considerably in their hypoxia tolerance, with some bivalves and worms capable of surviving brief exposure to near-zero oxygen concentrations through anaerobic metabolism, but unable to sustain this indefinitely without accumulating metabolic waste products that are themselves toxic at sufficient concentrations. The fossil record from this interval reflects these physiological realities in the distribution and preservation of organisms across different depositional environments. Sediment sections from deeper shelf environments show a progressive loss of diverse benthic fauna replaced by impoverished assemblages dominated by small, thin-shelled organisms, a pattern consistent with the selective survival of the most hypoxia-tolerant forms. In some sections, these impoverished assemblages are themselves replaced by barren laminated sediments, indicating that even the most tolerant benthic organisms eventually exceeded their physiological limits as oxygen concentrations continued to fall. The sedimentary record is, in this sense, a direct physical archive of a biological community, retreating upward and inward as its chemical environment contracted around it. The planktonic communities of the surface ocean were not immune to these pressures, despite their proximity to the atmosphere. Warming surface temperatures altered the density and viscosity of seawater in ways that affected the sinking rates of the organic particles that planktonic organisms depend upon for nutrition. Changes in ocean circulation disrupted the upwelling of nutrient-rich deep water that had historically sustained high planktonic productivity in certain regions. The base of the marine food web, the photosynthetic phytoplankton, and the zooplankton that grazed upon them was experiencing its own restructuring, with diversity declining and community composition shifting towards smaller, more opportunistic forms less capable of sustaining the energy flux that larger predators in the layers above them required. The interaction between surface productivity decline and deep ocean deoxygenation created a feedback that accelerated both processes simultaneously. As surface productivity declined, less organic material sank into the deep ocean. This reduced the food supply available to deep-water communities, but it also reduced the oxygen demand of decomposition in intermediate layers, a dynamic that might, in isolation, have partially offset deoxygenation. However, the simultaneous reduction in vertical circulation was so substantial that it overwhelmed this partial, compensating effect. Oxygen delivery to depth declined faster than oxygen demand decreased. The net result was continued and accelerating deoxygenation of the ocean interior, despite the reduction in the biological processes consuming that oxygen. What the late Permian Ocean was approaching, across this interval of compounding chemical and physical change, was a state that has no analogue in any ocean the modern world has experienced within human observation. The habitable volume of the global sea was shrinking from below, contracting from depth upward as anoxic and eosinic water masses expanded. It was shrinking from the perspective of thermal tolerance as temperatures climbed beyond the physiological range of organisms evolved in cooler than conditions. And it was shrinking chemically as acidification impaired calcification and altered the carbonate system that reef and shell building organisms depended upon. The ocean was not failing in one dimension. It was failing across several simultaneously. And the compounding nature of these failures meant that the stress experienced by marine communities was not simply additive. It was multiplicative, each pressure reducing the capacity of organisms to tolerate the others. Hydrogen sulfide is not a substance the ocean produces in abundance under normal conditions. In a well-oxygenated marine system, the sulfur cycle operates in a way that keeps this molecule effectively contained, generated in trace quantities within anoxic sediment-poor waters, then oxidized back into harmless sulfate before it can accumulate in the overlying water column. The chemistry is self-regulating as long as oxygen is present in sufficient concentration. To drive the oxidation reactions that neutralize hydrogen sulfide at the sediment-water interface, remove that oxygen and the regulatory mechanism fails. Hydrogen sulfide, produced continuously by sulfate-reducing bacteria, metabolizing organic material in anoxic sediments, begins to accumulate. It diffuses upward, and once it enters the water column in sufficient concentration, it does not simply remain a localized chemical curiosity. It becomes a toxin capable of restructuring the biological landscape of the entire ocean. The geochemical evidence for widespread hydrogen sulfide accumulation in the late Permian Ocean is preserved with unusual clarity in the sedimentary record. Biomarkers derived from green sulfur bacteria, specifically isoreneurotane and related compounds, molecular fossils of pigmented anaerobic photosynthesizers that require both sunlight and hydrogen sulfide to function, have been identified in Permian Triassic boundary sediments from multiple locations across the ancient Tethys Sea, the Panthalassic Ocean, and high-latitude basins. These organisms occupy an extremely narrow chemical niche. They can only exist where the chemocline, the boundary between oxygenated and sulfide, rich water, rises into the photic zone, the upper 200 meters of the ocean where sunlight penetrates. Their presence in the fossil record is therefore not merely evidence of anoxia at depth. It is direct evidence that hydrogen sulfide had ascended into shallow, sunlit water that had previously supported the full complexity of Permian marine life. The toxicity of hydrogen sulfide to aerobic organisms operates through a specific biochemical mechanism. The molecule binds to cytochrome C oxidase, the enzyme responsible for the final step of aerobic cellular respiration, the transfer of electrons to oxygen. At concentrations above approximately 2 micromoles per liter, this binding inhibits the enzymes sufficiently to impair cellular energy production. At higher concentrations, the inhibition becomes effectively complete, and cells are unable to generate the ATP required to sustain basic biological functions. For marine animals, fish, invertebrates, and any other organism dependent on aerobic metabolism. Exposure to hydrogen sulfide at these concentrations is rapidly lethal, regardless of the availability of dissolved ethyl oxygen in the surrounding water. The two chemical stressors were not simply co-occurring. Hydrogen sulfide rendered oxygen physiologically inaccessible, even where oxygen was still technically present. The expansion of oceanic water, anoxic and sulfide-rich, through the intermediate and shallow ocean did not proceed as a uniform front, advancing at a constant rate. It was spatially variable, driven by local differences in water column stratification, organic matter supply, and the geometry of ocean basins. Enclosed or semi-enclosed basins with restricted circulation, analogous to the modern Black Sea, would have transitioned to oceanic conditions earlier and more completely than open ocean regions with greater water mass exchange. The ancient Tethys Sea, a broad equatorial ocean formed by the partial separation of the supercontinent Pangaea, had regions of restricted circulation along its margins that made it particularly susceptible to early and severe eoxinia. Geochemical data from sections preserving Tethyan boundary sediments show some of the strongest and most geographically extensive signals of sulfide enrichment yet identified in the Permian-Triassic record. As hydrogen sulfide diffused upward through the water column, it encountered and moved through the communities of organisms still persisting in intermediate depths. The compressed and already stressed survivors of the hypoxic expansion described in earlier stages of ocean deterioration. For organisms already operating at the margins of their physiological tolerance due to elevated temperature and reduced oxygen, the addition of hydrogen sulfide toxicity was not a manageable incremental stress. It was a threshold event. Species that had persisted through the initial phases of deoxygenation by behavioral compression into shallower water now faced a rising toxic boundary advancing toward them from below, while thermal stress and reduced prey availability continued to operate from above and around them. The food web consequences of hydrogen sulfide expansion were not limited to direct toxicity. The molecule's entry into the photic zone had profound effects on primary productivity, the photosynthetic foundation of the entire marine food web. Hydrogen sulfide is toxic to most photosynthetic organisms, including the phytoplankton that dominated Permian surface water productivity. As euvinic water intermittently upwelled or mixed into surface layers during storm events or seasonal circulation changes, it delivered pulses of hydrogen sulfide directly into the zone of maximum biological productivity. These pulses killed phytoplankton communities across affected areas, temporarily collapsing the base of the food web and sending a deprivation signal upward through every trophic level dependent on that productivity. The atmospheric consequences of hydrogen sulfide production at this scale were also significant. Hydrogen sulfide is volatile. It crosses the ocean atmosphere interface and enters the atmosphere where it reacts with and depletes stratospheric ozone. Modeling studies examining the potential scale of hydrogen sulfide outgassing during the Permian-Triassic boundary interval suggest that ozone depletion from this source alone could have been substantial, potentially reducing the ozone column sufficiently to allow damaging levels of ultraviolet radiation to reach Earth's surface. Evidence consistent with elevated ultraviolet exposure at the boundary, including malformed and mutated plant spores preserved in terrestrial sediments from the same interval, provides indirect support for this hypothesis, though the precise contribution of oceanic hydrogen sulfide relative to other potential ozone-depleting substances released by the Siberian traps, volcanism remains an area of active research. What hydrogen sulfide represented, in the context of the late Permian marine crisis, was the transition of the ocean from a system under stress to a system actively generating its own poison. The anoxic deep ocean had become a chemical reactor, producing and releasing a molecule lethal to the aerobic life that still persisted in shallower water. The buffer that had historically separated this chemistry from the living ocean above it, the oxygen-dependent oxidation reactions at the sediment-water interface had been progressively dismantled by the same deoxygenation that was compressing habitable space from below. The ocean was no longer simply losing the conditions necessary to support life. It was acquiring the capacity to actively destroy it. The deep ocean of the late Permian was not entirely lifeless. That distinction is important because the narrative of environmental collapse can obscure a more complex biological reality, one in which certain organisms, shaped by evolutionary histories that had prepared them inadvertently for conditions approaching those now developing across the ocean interior, continued to persist and in some cases expand their ecological footprint as the aerobic world above them contracted. The deep sea has never been a hospitable environment by the standards of shallow water marine life. It is cold, dark, and perpetually removed from the photosynthetic productivity that drives surface ocean food webs. The organisms that inhabit it have always been adapted to extremity. What the late Permian crisis did was not eliminate the deep sea entirely. It transformed it, chemically, biologically, and spatially, into something that had no precise precedent in the preceding history of complex marine life. Prior to the onset of severe deoxygenation, the Permian seafloor at abyssal and bathyal depths, roughly below 201.00 meters respectively, supported communities of organisms adapted to low light, reduced temperature, and limited food supply. These communities were less diverse than their shallow water counterparts, but they were not simple. Deposit-feeding invertebrates processed organic material that sank from productive surface waters. Bacterial mats colonized areas of elevated organic input. Occasional larger predators moved through the darkness, exploiting whatever biological resources the deep environment offered. The deep sea was, in this period as in all others, a functional ecosystem, slower, sparser, and operating on different energetic principles than the reef and shelf communities above it, but structured and biologically active nonetheless. As oxygen concentrations declined through the water column and anoxic conditions expanded upward, from the deepest basins, the organisms that had occupied intermediate and deep water environments faced a bifurcating set of conditions. Those with aerobic metabolic requirements were eliminated as oxygen fell below their tolerance thresholds. Those capable of anaerobic or microaerobic metabolism, functioning at oxygen concentrations far below what surface-adapted organisms require, found themselves in an environment from which their aerobic competitors were progressively being removed. The ecological release produced by the elimination of aerobic fauna created space, in the most literal biological sense, for anaerobic and sulfur-based microbial communities to expand across the seafloor without the grazing pressure, physical disturbance, and competitive exclusion that bioturbating invertebrates had historically imposed. The microbial ecosystems that developed across the anoxic Permian seafloor were ancient in their metabolic logic, drawing on biochemical pathways that had dominated Earth's oceans for more than 2 billion years before the evolution of complex animal life. Sulfate-reducing bacteria consuming organic carbon and releasing hydrogen sulfide formed the metabolic foundation of these communities. Methanogens, archaea producing methane as a metabolic byproduct, processed organic material in the deepest, most reducing sediment layers. At the chemocline, where sulfide-rich anoxic water met the residual oxygen of overlying water masses, communities of sulfur-oxidizing bacteria developed. Exploiting the chemical energy available at this interface, in a process functionally analogous to, but chemically distinct from, the photosynthesis occurring in sunlit surface waters far above. These chemolithotrophic communities, organisms deriving energy from inorganic chemical reactions rather than sunlight or the consumption of organic material produced by photosynthesis, represent one of the more extraordinary aspects of the late Permian deep ocean. They did not depend on surface productivity. They did not require oxygen. They existed in a chemical regime that was lethal to virtually every animal that had populated the Permian Sea, and they thrived within it. Their expansion across the deep seafloor during this interval is documented in biomarker records and isotopic signatures preserved in boundary sediments, chemical fingerprints of metabolic processes that leave distinctive molecular traces in the rock record even after hundreds of millions of years of burial and diagenesis. The physical environment of the deep late Permian Ocean reflected its chemical transformation in ways that have been perceptible even without biological analysis. In oxygenated deep-sea environments, the seafloor is constantly disturbed by the burrowing, feeding, and movement of benthic organisms, a process called bioturbation that physically mixes sediment layers and prevents the preservation of fine lamination. The transition to anoxic and aphinic conditions eliminated bioturbation by eliminating the organisms responsible for it, and the sedimentary record responds immediately and visibly. Laminated sediments, thin, undisturbed layers of fine material accumulating in an environment where nothing lives to disturb them. Replace the homogenized, bioturbated sediment textures characteristic of aerobic seafloor conditions. This transition, visible in outcrop sections from Permian-Triassic boundary deposits worldwide, is one of the most direct and physically unambiguous records of biological absence preserved in the geological record. At intermediate depths, where the chemocline intersected with remnant oxygenated water, the boundary between the aerobic and anaerobic ocean was not a sharp line but a gradient, a zone of rapidly changing chemical conditions across which different organisms occupied different chemical niches in close vertical proximity. In the modern ocean, analogous chemocline communities exist in restricted basins, such as the Black Sea and certain Norwegian fjords, and they demonstrate considerable structural complexity despite their unusual chemistry. By analogy, the expanding chemocline of the late Permian Ocean likely supported a vertically stratified community of chemolithotrophic bacteria, anaerobic protists, and other microorganisms occupying specific positions along the oxygen sulfide gradient. This was not the diverse, animal-dominated community of the healthy Permian Sea. But it was not biological emptiness either. It was a different kind of ocean, one governed by chemistry rather than by the ecological relationships of predation, competition, and coevolution that had structured Permian marine communities for hundreds of millions of years. The deep ocean of the late Permian was, in a meaningful sense, reverting. The chemical conditions expanding through its interior were more similar to those of the Archean Ocean, the ocean of a world before complex animal life, than to anything that had existed during the Phanerozoic, the eon of visible, complex life. This reversion was not total and it was not permanent, but its spatial extent, its chemical intensity, and its biological consequences were sufficient to constitute a fundamental reorganization of how the ocean interior functioned. A reorganization that would propagate its effects upward through the water column and outward into every corner of the marine world, still attempting to sustain the biological complexity of a system that the ocean's chemistry was systematically dismantling. The coastlines of the late Permian world were not uniform. They traced the margins of a supercontinent, Pangaea, whose single, vast landmass produced a coastline of extraordinary geographic variety, ranging from shallow tropical shelves, bathed in warm, nutrient-rich water, to higher latitude margins where cooler upwelling sustained different but equally productive biological communities. These coastal zones had historically been among the most biologically productive environments on Earth, concentrating life at the interface between terrestrial nutrient input and marine photosynthetic productivity. River systems draining the continental interior delivered dissolved minerals and organic material to nearshore environments, sustaining dense planktonic communities that in turn supported the layered food webs of fish, invertebrates, and larger predators that characterized healthy coastal marine ecosystems. As the environmental pressures building through the ocean interior began to propagate into shallow coastal waters, these environments, precisely because of their biological density and the concentration of life they supported, became the sites of some of the most visible and ecologically devastating consequences of the marine crisis. The shallow shelf environments adjacent to coastlines were among the last regions of the ocean to experience the full severity of deoxygenation, but when that threshold was crossed, the biological impact was disproportionate to the physical change, because the communities concentrated in these environments had nowhere to retreat. Unlike pelagic organisms capable of ranging across open ocean in search of tolerable conditions, coastal and shelf-associated species were constrained by geography, by the physical structure of reef and seafloor habitats they depended upon, and by the simple fact that the conditions deteriorating around them were deteriorating simultaneously across the entire extent of their available habitat. The fossil record from coastal and shallow shelf depositional environments preserves the consequences of this convergence with a resolution that deeper water sediments rarely achieve. Nearshore sediment sections from the Permian-Triassic boundary, examined across multiple paleocontinental regions, including the margins of the ancient Tethys Sea, the western margin of Pangaea, and high-latitude shelf sections from what is now Greenland and Siberia, show a consistent pattern, a transition from fossiliferous, biologically diverse sediment to impoverished or barren layers occurring within stratigraphic intervals representing, in some sections, as little as a few thousand years. The diversity collapse recorded in these sections is not gradual. It is abrupt by geological standards, suggesting that the biological communities of coastal environments did not fade incrementally, but crossed ecological tipping points beyond which community structure could not be maintained. Among the most ecologically significant consequences of coastal marine collapse was the disruption of predator-prey relationships that had structured these communities across millions of years. Apex predators in coastal environments, large fish, early marine reptiles and cephalopods operating in shallow water, depended on prey populations that were themselves dependent on the structural complexity of reef and seafloor habitats and on the planktonic productivity of nearshore surface water. As reef frameworks degraded, as benthic invertebrate communities collapsed, and as planktonic productivity declined in response to warming and chemical disruption, the prey base available to coastal predators contracted from multiple directions simultaneously. The energetic consequences for large predators were direct and measurable in principle, even where the fossil record captures only their ultimate disappearance rather than the process of their decline. Large marine predators require substantial and consistent caloric input to maintain body mass and reproductive capacity. A reduction in prey density below a critical threshold does not simply reduce predator growth rates. It triggers a cascade of physiological and behavioral consequences, including increased foraging range, reduced reproductive investment, elevated metabolic stress, and eventually population decline as mortality rates exceed reproductive replacement. In coastal environments where the spatial extent of suitable habitat was itself shrinking due to hypoxic expansion and reef degradation, the increased foraging ranges required by stressed predators brought them into direct competition with one another across a diminishing resource base. The physical evidence of mass mortality in coastal environments is preserved in several forms across Permian-Triassic boundary sections. Concentrations of disarticulated skeletal material, bones and shells accumulated in sedimentary layers without the spatial organization, characteristic of living community assemblages, indicate episodes of elevated mortality not attributable to normal predation or individual senescence. These accumulations, sometimes referred to informally as death assemblages, represent the physical residue of biological communities collapsing faster than decomposition. Scavenging and sedimentary reworking can disperse the material evidence of that collapse. Their presence in coastal sections from multiple geographic regions indicates that mass mortality events were not locally restricted phenomena but reflected ocean-wide deterioration, expressing itself most visibly at the biologically dense margins of the sea. Coastal ecosystems also experienced from terrestrial sources that amplified the marine stressors already operating from within the ocean. The same volcanic forcing, driving ocean warming and deoxygenation, was simultaneously altering terrestrial environments, increasing wildfire frequency, disrupting vegetation cover, and accelerating erosion across continental landscapes. Increased erosion delivered elevated sediment loads to coastal environments through river systems, reducing water clarity, smothering benthic habitats, and altering the nutrient balance of nearshore waters in ways that favored opportunistic microbial blooms over the structured planktonic communities that healthy coastal food webs depended upon. Harmful algal blooms, dense proliferations of phytoplankton species that produce toxins or consume oxygen in quantities lethal to surrounding fauna, are a likely consequence of this nutrient disruption, though their direct preservation in the fossil record is limited by the poor preservation potential of soft-bodied algal material. The coastlines of the late Permian were, by the peak of the environmental crisis, environments in the process of biological evacuation. The communities that had inhabited them, the dense, layered, ecologically complex assemblages of reef fish, benthic invertebrates, planktonic organisms, and larger predators that had characterized these environments for tens of millions of years, were being dismantled by the convergence of thermal stress, chemical disruption, habitat degradation, and food web collapse operating simultaneously across every trophic level. What remained in the sedimentary record after this dismantling is not simply an absence of fossils. It is a structured record of biological simplification, the replacement of complex, diverse communities by sparse assemblages of tolerant generalists, and eventually by the laminated, fossil-poor sediments that mark the complete withdrawal of animal life from environments that had once been among the most productive on Earth. The ocean and the atmosphere have never been independent systems. They exchange gases, energy, and chemical compounds across their shared interface continuously, and the state of one exerts measurable influence on the state of the other across timescales ranging from hours to millions of years. During the late Permian environmental crisis, this coupling became a mechanism of amplification, a pathway through which the deteriorating chemistry of the ocean propagated its consequences upward into the atmosphere and through the atmosphere outward across the surface of the entire planet. The sky above the dying Permian Ocean was not a neutral backdrop to the marine catastrophe unfolding below it. It was an active participant, receiving the chemical outputs of an ocean in collapse and returning altered conditions to both the sea and the land in ways that extended the reach of the crisis far beyond the water's edge. The most direct atmospheric consequence of the ocean's chemical transformation was the outgassing of volatile compounds produced in abundance by the expanding anaerobic ecosystems of the deep and intermediate ocean. Hydrogen sulfide, generated continuously by sulfate-reducing bacteria across the vast anoxic seafloor, is not fully retained within the water column. At the ocean's surface, where wind-driven mixing and gas exchange with the atmosphere occur constantly, hydrogen sulfide crosses the air-sea interface and enters the lower atmosphere. Under normal oceanic conditions, this flux is negligible. The quantity of hydrogen sulfide produced in isolated anoxic sediments and transported to the surface is too small to accumulate meaningfully in an atmosphere where it is rapidly oxidized by reaction with hydroxyl radicals. But under the conditions of the late Permian, where oceanic water masses had expanded to cover large areas of the ocean interior, and in some regions had ascended into the photic zone, the flux of hydrogen sulfide from ocean to atmosphere increased by estimated orders of magnitude above background levels. The atmospheric chemistry consequences of this elevated hydrogen sulfide flux operated through several interconnected pathways. In the lower atmosphere, hydrogen sulfide reacts with oxygen and solar radiation to produce sulfur dioxide and eventually sulfate aerosols, fine particles that scatter incoming solar radiation and can contribute to surface cooling on regional scales. This aerosol production from oceanic hydrogen sulfide added a chemically distinct sulfur burden to an atmosphere already receiving substantial sulfur dioxide from the Siberian Traps volcanism, creating a complex atmospheric chemistry in which multiple sulfur species were simultaneously present at elevated concentrations. More significant in terms of biological impact was the fate of hydrogen sulfide reaching the stratosphere. The stratosphere contains the ozone layer, a region of elevated ozone concentration between approximately 15 and 35 kilometers altitude that absorbs incoming ultraviolet radiation in the wavelength range most damaging to biological molecules, particularly DNA. Hydrogen sulfide and its atmospheric oxidation products can participate in catalytic ozone destruction reactions, reducing ozone column density and allowing elevated ultraviolet flux to reach Earth's surface. Modeling studies examining the potential scale of oceanic hydrogen sulfide outgassing during the Permian-Triassic boundary interval, combined with the additional ozone-depleting halogens released by the Siberian Traps volcanism, suggest that ozone column reductions of 50% or more over equatorial regions are physically plausible under peak boundary conditions, reductions far exceeding anything observed in the modern atmosphere, even during the most severe episodes of anthropogenic ozone depletion. The biological consequences of ultraviolet radiation at these elevated levels would have operated across both marine and terrestrial environments. In the surface ocean, ultraviolet radiation penetrates to depths of several meters in clear water, and elevated UV flux directly damages the DNA and photosynthetic machinery of phytoplankton, the photosynthetic organisms responsible for the base of the marine food web and for approximately half of global oxygen production. Evidence consistent with elevated ultraviolet stress at the Permian-Triassic boundary is preserved in the terrestrial fossil record in the form of malformed and mutated pollen and spores, specifically spores with irregular wall structures and abnormal morphology that are indicative of disrupted cell division consistent with DNA damage from elevated UV exposure. These malformed spores have been identified in boundary sections from multiple geographic regions, providing indirect but geographically widespread evidence that ultraviolet stress was a real and significant component of the boundary environmental crisis rather than a modeled possibility. The warming ocean also contributed to atmospheric modification through the outgassing of carbon dioxide and methane from marine sources. As ocean temperatures rose, the solubility of carbon dioxide in seawater declined, reducing the ocean's capacity to absorb atmospheric carbon dioxide and potentially reversing it, converting the ocean from a net carbon sink to a net carbon source across some regions. Methane produced by methanogenic archaea in anoxic seafloor sediments and potentially from destabilized methane hydrate deposits on continental margins. Ice-like structures in which methane is trapped within a water ice lattice stable only within specific temperature and pressure ranges, added additional greenhouse forcing to an atmosphere already substantially enriched in carbon dioxide by volcanic emissions. The destabilization of methane hydrates is not universally accepted as a significant factor in the Permian-Triassic boundary warming, and the evidence for their large-scale dissociation at this time remains debated, but the physical mechanism is well established and the boundary conditions are consistent with at least partial destabilization across shallow, continental margin deposits. The atmospheric changes propagating from the ocean's collapse affected the hydrological cycle in ways that further stressed both marine and terrestrial ecosystems. Warming ocean surface temperatures increased evaporation rates, loading the atmosphere with water vapor, itself a greenhouse gas, and altering precipitation patterns across continental interiors. Evidence from terrestrial sediment sections of late Permian age indicates increased aridity across portions of the Pangaean interior, consistent with the disruption of precipitation patterns by altered ocean atmosphere heat exchange. Coastal regions, by contrast, may have experienced intensified precipitation and storm activity driven by elevated sea surface temperatures, increasing erosive runoff into already stressed coastal marine environments. What the atmosphere above the late Permian Ocean represented was a system simultaneously receiving chemical outputs from a deteriorating ocean below and a volcanically active continental region to the north, integrating these inputs into altered radiation, temperature, and precipitation conditions, and returning those altered conditions to the surface in ways that closed feedback loops operating across the full extent of the planet. The sky was not simply changing in response to what the ocean was doing. It was changing in ways that made the ocean's situation worse, and the ocean's worsening situation was in turn altering the sky further. The planetary system had entered a regime of coupled feedbacks in which the distinction between cause and consequence was becoming increasingly difficult to maintain. There is a threshold in any complex system beyond which the loss of individual components begins to accelerate the loss of others, where the redundancy that had historically absorbed stress is exhausted and the system's internal architecture begins to work against its own survival. The Permian marine ecosystem reached that threshold not at a single moment identifiable in the rock record, but across an interval of accelerating biological collapse that geologists and paleontologists have worked for decades to characterize with increasing precision. What the evidence collectively describes is not a gradual, continuous decline terminating in extinction, but a system that deteriorated in stages, stabilized partially between pulses of environmental forcing, and then crossed into irreversible collapse as the cumulative damage to its biological infrastructure exceeded its capacity for ecological recovery. The extinction that defines the Permian-Triassic boundary is the largest in the history of complex animal life. Current estimates, derived from analysis of fossil collections across hundreds of stratigraphic sections worldwide and corrected for sampling biases in the rock record, indicate that approximately 81 to 96% of all marine species were eliminated, a range reflecting genuine uncertainty in the completeness of the fossil record rather than disagreement about the fundamental magnitude of the event. At the upper end of these estimates, the Permian-Triassic extinction eliminated a greater proportion of marine biodiversity than any other known event in the 540 million year history of the Phanerozoic, the eon that encompasses all complex animal life on Earth. The scale is not easily rendered into intuitive terms. It represents the elimination of biological lineages that had persisted across hundreds of millions of years, many of which had survived previous extinction events that were themselves considered catastrophic by any ordinary measure. The acceleration of extinction across the boundary interval was not uniform across all taxonomic groups or all geographic regions. Some groups had been declining for millions of years before the boundary, their diversity eroding gradually as environmental conditions deteriorated through the late Permian. Others persisted with relatively little apparent change until very close to the boundary horizon, then disappeared abruptly, within intervals that the best available radiometric dating constrains to less than 100,000 years, and in some sections, potentially less than 60,000 years. This temporal pattern of prolonged background decline followed by rapid terminal collapse is consistent with a system in which gradual environmental deterioration progressively reduced ecological resilience, leaving communities increasingly vulnerable to the acute environmental perturbations associated with peak volcanic activity from the Siberian traps. The groups most severely affected were those most deeply integrated into the structural and functional architecture of the Permian marine ecosystem. Rugose and tabulate corals, the primary reef-building organisms of earlier Paleozoic seas, did not survive the boundary at all, their complete extinction eliminating reef-building capacity from the ocean for millions of years into the Triassic. Brachiopods, which had been among the most diverse and abundant marine invertebrates for hundreds of millions of years, lost an estimated 80% or more of their species diversity. Bryozoans, crinoids, blastoids, and fusolinid foraminifera, organisms that had been constituent members of marine communities across the entire Paleozoic, were either eliminated entirely or reduced to small fractions of their former diversity. The trilobites, which had inhabited the ocean for over 270 million years by the late Permian, did not survive. The loss of these groups was not simply a taxonomic subtraction. Each represented a functional role within the marine ecosystem, a set of ecological processes that other organisms depended upon, directly or indirectly, for food, habitat structure, or the chemical processing of organic material. The elimination of reef-building organisms removed the physical framework within which thousands of associated species had lived. The collapse of filter-feeding invertebrate communities disrupted the processing of organic particles in the water column, altering the flux of material through the food web. The loss of diverse echinoderms and other bioturbators reduced the physical mixing of seafloor sediments, diminishing the recycling of nutrients from sediment-poor waters back into the overlying water column. Each functional loss cascaded through the system, reducing the ecological services available to surviving organisms and making the remaining community progressively less capable of buffering against continued environmental stress. The geographic pattern of extinction across the boundary adds spatial resolution to the taxonomic record. Tropical regions, where water temperatures were already at the upper margins of tolerance for many organisms before the onset of significant warming, experienced some of the most severe extinction intensities. The ancient Tethys Sea, the equatorial ocean that separated the northern and southern portions of Pangaea, was a center of both Permian biodiversity and Permian extinction, its warm, shallow margins losing biological complexity at rates that exceed those recorded in higher latitude sections. Higher latitude regions, where absolute temperatures remained below the lethal thresholds reached in tropic waters for longer into the extinction interval, show evidence of somewhat attenuated extinction intensity in some taxonomic groups, though the ultimate outcome across all latitudes was the same: biological impoverishment on a scale without precedent in the preceding history of complex marine life. The tempo of extinction, where it can be resolved at sufficient temporal resolution, reveals a pattern of multiple pulses rather than a single event. Carbon isotope records from boundary sections, which track changes in the global carbon cycle and by proxy in the productivity and composition of marine biological communities, show several negative excursions, rapid shifts toward isotopically lighter carbon values distributed across the extinction interval. Each excursion corresponds to a disruption of the marine carbon cycle consistent with a pulse of elevated volcanic forcing, ocean warming, or biological productivity collapse. Between excursions, the isotopic record shows partial stabilization, consistent with transient intervals of reduced environmental stress during which surviving community may have begun limited ecological recovery. These recovery intervals were insufficient. Each subsequent pulse of environmental forcing found a biological community already depleted by the previous one, with less diversity, less functional redundancy, and less capacity to absorb the next perturbation without further collapse. The ocean that entered the terminal phase of the Permian-Triassic extinction was not the ocean that had existed at the start of environmental deterioration. It had already lost substantial diversity, already experienced the collapse of its reef systems, already contracted its habitable volume, already been invaded by toxic chemistry from below. What remained was a diminished and stressed residual community operating in an ocean that was simultaneously too warm, too acidic, too depleted of oxygen, and in significant regions actively poisoned by hydrogen sulfide. The extinction that followed was not inflicted upon a healthy system by an external shock. It was the terminal stage of a system that had been progressively dismantled, from its chemical foundation upward, across tens of thousands of years, until what remained was too reduced in complexity and too compromised in function to persist. At the peak of the Permian-Triassic boundary crisis, the global ocean had been transformed into an environment that was, across the majority of its volume, incompatible with the forms of life that had inhabited it for hundreds of millions of years. This was not hyperbole or geological shorthand for a severe but ultimately manageable disruption. The chemical, thermal, and biological conditions that characterized the ocean at the boundary horizon represented a genuine planetary emergency, a state in which the foundational parameters of the marine environment had shifted so far outside the range within which complex animal life had evolved that survival, rather than ecological function, became the only meaningful biological currency. The spatial extent of the environmental transformation is perhaps the most important dimension to establish precisely because it determines the degree to which the crisis was a regional catastrophe versus a global one. Geochemical proxy data from Permian-Triassic boundary sections, encompassing oxygen isotopes, carbon isotopes, sulfur isotopes, nitrogen isotopes, and the distribution of redox-sensitive trace metals in carbonate and shale sequences, have been collected from sections representing every major ocean basin and continental margin of the late Permian world. The consistency of signal across these geographically dispersed sections is striking. Anoxic and oceanic conditions, elevated temperatures, disrupted carbon cycling, and collapsed benth communities are not features of a particular basin or a particular latitude. They are features of the global ocean, expressed with varying intensity across different regions but present, in some form, essentially everywhere the rock record has been examined in sufficient detail. The habitable volume of the ocean at the boundary peak has been estimated through the integration of these proxy records with ocean circulation, models calibrated to late Permian boundary conditions. These reconstructions suggest that severely oxygen-depleted water, defined as containing less than 2 milliliters of dissolved oxygen per liter, may have occupied between 40 and 80% of the total ocean volume during peak anoxic conditions. The range reflects genuine uncertainty in both the proxy reconstructions and the model parameters, but even the lower bound of this estimate represents an ocean in which the majority of the water column was physiologically hostile to most aerobic marine animals. The upper bound describes an ocean in which habitable space had been reduced to a thin surface veneer, a layer of oxygenated water, perhaps tens to low hundreds of meters deep, floating above an interior that was effectively lethal. Within this compressed habitable layer, the biological communities that had survived the initial phases of environmental deterioration were operating under conditions of extreme ecological stress. Temperature in tropical surface waters had reached an estimated 35 to 40 degrees Celsius in some reconstructions, a range that exceeds the thermal tolerance limits of virtually all modern marine animals and that, by analogy, would have been lethal or severely impairing for most Permian marine fauna. The combination of elevated temperature and reduced dissolved oxygen created a condition sometimes described in modern marine biology as the oxygen and capacity-limited thermal tolerance effect, a phenomenon in which warming reduces both the oxygen available in water and the physiological capacity of organisms to extract and utilize that oxygen, producing a compound impairment far more severe than either stressor would produce in isolation. For Permian marine animals already at the margins of their physiological tolerance, this compound effect was, for most species, unsurvivable across sustained exposure. The collapse of ancient food chains at the boundary peak was not simply the subtraction of individual species from a functioning system. It was the unraveling of the relational architecture that had structured marine ecological communities across the entire Paleozoic. The concept of a food chain, while useful as a simplified representation, understates the actual complexity of the trophic relationships involved. Marine ecosystems are better understood as food webs. networks of feeding relationships in which energy flows through multiple pathways simultaneously, and in which the loss of any single node affects the stability of connections far removed from the point of loss. The Permian marine food web, refined across hundreds of millions of years of coevolution, had been one of the most complex trophic networks in Earth history. Its unraveling at the boundary proceeded not as the sequential removal of species from a stable structure, but as the progressive degradation of the network itself. Each species loss reducing the connectivity and resilience of the remaining system, making subsequent losses more likely and more ecologically disruptive. The microbial communities that expanded across the anoxic and eosinic ocean at the boundary peak were not simply filling ecological space vacated by the collapse of animal communities. They were actively modifying ocean chemistry in ways that perpetuated, and in some respects, intensified the conditions driving animal extinction. Sulfate-reducing bacteria, producing hydrogen sulfide across the vast anoxic seafloor and water column, maintained eosinic conditions in deep and intermediate waters that prevented the recolonization of these environments by aerobic organisms even during intervals of reduced volcanic forcing. Methanogenic archaea contributed continued greenhouse, forcing through methane outgassing, sustaining elevated atmospheric temperatures that kept ocean surface waters above the thermal tolerance thresholds of most surviving marine fauna. The microbial ocean was, in this sense, self-sustaining, maintaining through its own metabolic activity the chemical conditions that excluded the aerobic animal communities that might otherwise have begun to recover. The ancient food chains of the Permian Ocean had included linkages operating across timescales and spatial scales that are not immediately obvious from taxonomic lists of extinct species. The productivity of surface waters had depended on the upwelling of nutrients from depth, a process driven by ocean circulation that was itself disrupted by the thermal stratification of the boundary ocean. The structural complexity of reef environments had provided nursery habitat for juvenile fish and invertebrates, a function eliminated by reef collapse. The bioturbation of seafloor sediments by burrowing invertebrates had recycled nutrients from sediment pore waters back into the water column, a process terminated by the elimination of benthic fauna from anoxic seafloor environments. Each of these ecological services, productivity, habitat structure, nutrient recycling, had been integral to the functioning of the Permian marine food web, and each was disrupted or eliminated by the boundary crisis in ways that compounded the direct physiological impact of temperature, anoxia, and toxicity on individual organisms. What the boundary ocean represented, at its worst, was a system that had crossed from one stable ecological state into another. From the aerobic, animal-dominated, ecologically complex ocean of the Paleozoic into a simpler, microbe-dominated, chemically reducing system more similar in its fundamental character to the oceans of the Precambrian than to anything that had existed during the 500 million years of complex animal life preceding it. The transition was not permanent. The ocean would eventually recover, but the depth and duration of the collapse and the biological cost extracted in the process would shape the trajectory of marine life for millions of years into the future. Not long, you said, continue but max 7,000 characters. Not everything died. That fact, simple as it appears in statement, carries considerable scientific weight, because the organisms that survived the Permian-Triassic boundary crisis did not do so randomly. Their survival was not the product of fortunate coincidence distributed arbitrarily across the tree of life. It was, in the aggregate, structured, shaped by physiological tolerances, ecological flexibility, geographic circumstance, and body size in ways that, when examined systematically across the fossil record, reveal coherent patterns of selectivity. Understanding which organisms survived, and why, is not simply an exercise in cataloguing the remnants of a catastrophe. It is a window into the biological properties that determine resilience under conditions of extreme and sustained environmental stress. conditions that pushed the ocean closer to biological silence than any event in the preceding history of complex animal life. The most consistent predictor of survival across taxonomic groups was physiological tolerance of low oxygen and elevated temperature. Organisms whose aerobic metabolism could function at oxygen concentrations well below those required by more sensitive species had a measurable survival advantage in an ocean where habitable space had been compressed into a thin, thermally stressed surface layer. This tolerance was not uniformly distributed across the animal kingdom. It correlated, broadly, with metabolic rate and body size. Smaller organisms with lower absolute oxygen demands per individual were better positioned to persist in hypoxic conditions than larger organisms requiring greater oxygen flux to sustain their cellular machinery. The fossil record from earliest Triassic marine sediments, the sediments immediately above the extinction horizon, consistently shows a dramatic reduction in the average body size of surviving fauna relative to late Permian assemblages, a phenomenon sometimes referred to as the Lilliput effect, in which post-extinction survivors are systematically smaller than their pre-extinction counterparts or ancestors. The Lilliput effect is not simply an artifact of ecological disruption. It reflects active physiological selection operating through the boundary crisis. Larger bodies require more oxygen, more food, and more stable environmental conditions to sustain. In an ocean simultaneously depleted of oxygen, reduced in food availability through the collapse of primary productivity, and thermally destabilized, large body size became a liability rather than an advantage. Species and lineages that included smaller-bodied individuals, or that were capable of reducing body size across generations in response to resource limitation, were more likely to leave descendants in the earliest Triassic than those committed to large-bodied physiological strategies by their evolutionary history. Among the marine groups that demonstrated measurable survival through the boundary, bivalves merit particular attention. Unlike brachiopods, which superficially resemble bivalves but suffered catastrophic losses at the boundary, many bivalve lineages possessed physiological and behavioral characteristics that conferred significant resilience. Bivalves are capable of closing their shells and entering a state of reduced metabolic activity during periods of environmental stress, effectively suspending their oxygen demand for limited intervals. Some bivalve species can tolerate hypoxic conditions through partial anaerobic metabolism, producing metabolic byproducts that are toxic in accumulation but survivable over short intervals. Additionally, bivalves tend to have broad environmental tolerances relative to more specialized filter feeders. They occur across a wide range of depths, temperatures, and substrate types, making them less dependent on the specific conditions of any single habitat type that might be eliminated by the boundary disruption. The result of these combined characteristics is that bivalves not only survive the Permian-Triassic boundary in greater proportional diversity than brachiopods, but expanded significantly in the earliest Triassic, occupying ecological space vacated by the extinction of less tolerant groups. Gastropods, snails and their relatives, similarly demonstrated resilience, with multiple lineages persisting through the boundary and diversifying in the earliest Triassic. Their survival likely reflects a combination of broad dietary flexibility, tolerance of variable environmental conditions, and the ability of some lineages to exploit terrestrial and freshwater environments as refugia during the most severe phases of marine disruption. The distinction between strictly marine and euryhaline, or amphibious lineages, may have been ecologically significant at the boundary. Organisms capable of exploiting nearshore, brackish, or even terrestrial habitats had access to refugia that obligate open ocean species did not. Certain fish lineages persisted through the boundary, though fish diversity was substantially reduced relative to late Permian levels. The survivors were predominantly small-bodied, generalist feeders associated with shallow coastal or reef margin environments. Precisely the habitat, types that, while severely degraded, retained some degree of oxygenation and biological productivity longer than deeper water environments. Early actinopterygian fish, ray-finned fish, the group that would eventually come to dominate Mesozoic and Cenozoic marine ecosystems, were among the survivors, their persistence through the boundary establishing the evolutionary foundation for the subsequent diversification of the group that now accounts for approximately half of all living vertebrate species. Geographic refugia played a significant role in structuring which populations and lineages survived. The boundary crisis, though global in its reach, was not spatially uniform in its intensity. Higher latitude regions, where absolute water temperatures remained somewhat below the extreme values reached in tropical oceans, may have functioned as refugia for thermally sensitive organisms. Evidence from earliest Triassic fossil assemblages in high-latitude sections from what are now Arctic and Antarctic regions shows somewhat higher survival rates for certain taxonomic groups relative to coeval tropical sections, consistent with the hypothesis that thermal stress was a primary driver of extinction intensity in equatorial regions. Shallow water environments adjacent to major freshwater inputs, river deltas and estuaries, may have provided locally diluted salinity and slightly different chemical conditions that buffered some organisms against the most severe effects of ocean acidification. The survivors of the Permian-Triassic boundary crisis inherited an ocean that was, by every ecological measure, profoundly impoverished relative to the one that had existed before the crisis. The reef frameworks were gone, the diverse benthic communities were gone, the apex predators that had structured open water food webs were largely gone. What remained was a simplified, ecologically sparse system dominated by opportunistic generalists operating in an ocean still chemically disturbed, still warmer than conditions that had prevailed through most of the Permian, and still recovering from the disruption of the circulation and nutrient cycling systems that biological productivity depended upon. Survival through the boundary was not arrival in a functioning world. It was emergence into an ecological vacuum, one that would take millions of years to refill, and that would be refilled, when recovery eventually came, by a biological community fundamentally different in its composition and structure from the one the extinction had destroyed. The earliest Triassic ocean was not recovering. That distinction between an ocean that had survived a catastrophe and one that was actively rebuilding from it is important to establish precisely, because the two conditions are ecologically very different, and the evidence from the geological record indicates clearly that the ocean immediately following the Permian-Triassic boundary was, for a sustained interval, neither biologically diverse nor ecologically functional in any sense comparable to the systems that had preceded the extinction. The survivors of the boundary crisis were present, but survival and recovery are not the same process. Recovery requires not merely the persistence of individual organisms or lineages, but the reconstruction of the ecological relationships. Feeding, interactions, habitat dependencies, and biogeochemical functions that transform a collection of surviving species into a functioning ecosystem. That reconstruction in the aftermath of the Permian-Triassic extinction was delayed, interrupted, and incomplete a crisis that current estimate date placed approximately 5 to 10 million years following the boundary horizon. The sedimentary record of the earliest Triassic is, in many sections, one of the most biologically impoverished in the entire Phanerozoic. The characteristic fossil assemblages of this interval, sometimes referred to informally as the aftermath fauna, are dominated by a small number of opportunistic, generalist species occurring in high abundance but low diversity. This combination of high abundance and low diversity is itself ecologically informative. It is the biological signature of a system in which ecological competition has been largely eliminated by extinction, allowing the few surviving lineages to expand without the constraint of the diverse competitor and predator communities that had historically regulated their population sizes. The aftermath fauna were not thriving in any meaningful sense. They were expanding into a vacuum, temporarily freed from the competitive pressures of a complex ecosystem, but inhabiting an ocean that remained chemically and thermally hostile to the reconstruction of that complexity. Among the most geographically widespread and taxonomically consistent members of the aftermath fauna was a small bivalve, Chlorea, which appeared in earliest Triassic marine sediments across multiple paleocontinental regions within a geologically brief interval following the extinction horizon. Its rapid geographic expansion reflects both the ecological opportunity created by the elimination of competing benthic fauna and the relatively tolerant physiology of bivalves in low oxygen conditions. Chlorea and related disaster taxa, a term applied to organisms that expand dramatically in the immediate aftermath of mass extinctions by exploiting vacated ecological space, are not indicators of biological recovery. They are indicators of biological simplification, their dominance in earliest Triassic assemblages reflecting the absence of the diverse communities that would, in a recovering system, have constrained their expansion. The physical environment of the earliest Triassic ocean continued to present conditions hostile to ecological reconstruction for millions of years following the boundary. Ocean temperatures remained elevated. Some proxy records indicate that equatorial sea surface temperatures in the earliest Triassic were as high or higher than those at the boundary peak, suggesting that the thermal forcing driving the extinction was not immediately relieved by the cessation of peak Siberian traps volcanic activity. Carbon isotope records from earliest Triassic marine sediments show continued volatility, repeated negative excursions indicating ongoing disruption of the marine carbon cycle, rather than the smooth return towards stable values that would be expected if environmental conditions were recovering monotonically. The ocean was not stabilizing in the immediate aftermath of the extinction. It was continuing to fluctuate, delivering repeated pulses of chemical and thermal stress to biological communities already severely impoverished by the boundary crisis itself. Reef ecosystems, the most structurally complex and biologically diverse environments of the Permian Ocean, were absent from the earliest Triassic marine record for an interval of approximately 4 to 6 million years following the extinction boundary. This reef gap, documented across multiple geographic regions and representing the longest interval of reef absence in the Phanerozoic record, reflects both the complete elimination of the primary Paleozoic reef-building organisms at the boundary and the inability of potential replacement reef builders to establish themselves in ocean conditions that remained too warm, too acidic, and too chemically disturbed to support the calcification rates required for reef framework construction. The physical substrates that had supported Permian reefs, the shallow carbonate platforms of continental margins, were present. The organisms capable of rebuilding upon them were not, and would not be, for millions of years. The seafloor of the earliest Triassic provides additional evidence of the depth of ecological disruption through the continued absence of bioturbation in many sections. The laminated sediments characteristic of the boundary anoxic event persist into lower Triassic strata in some sections, indicating that bottom water oxygen concentrations in certain regions remained below the threshold required to support burrowing invertebrates for an extended interval following the boundary. Where bioturbation does reappear in earliest Triassic sections, it does so in a simplified form. Shallow, simple burrow traces characteristic of small, low-diversity infaunal communities rather than the complex, deeply penetrating bioturbation structures produced by the diverse benthic fauna of Permian seafloor environments. The return of bioturbation to the sedimentary record is one of the proxy indicators used to track the gradual recovery of benthic oxygen conditions, and its absence or simplification in earliest Triassic sections marks the temporal extent of seafloor environmental disruption. The chemical legacy of the boundary crisis extended into the water column through the continued, if diminishing, influence of the anaerobic microbial ecosystems that had expanded during the extinction interval. Biomarker evidence for green sulfur bacteria, the molecular indicators of oceanic conditions in the photic zone, persist into earliest Triassic. Sediments in some sections, indicating that sulfide-rich water continued to impinge on shallow, sunlit ocean layers after the extinction boundary. The duration and geographic extent of this post-boundary Eutenia varied by region, but its persistence demonstrates that the chemical transformation of the ocean was not simply reversed by the removal of peak volcanic forcing. The ocean's chemistry had been reorganized at a fundamental level, and its return to the oxidized, aerobically structured state required to support complex animal life was a process measured in millions of years rather than thousands. What the earliest Triassic ocean represented was the physical and chemical residue of the most severe biological disruption in the history of complex marine life. An environment still shaped by the processes that had driven extinction, still hostile in fundamental ways to the ecological reconstruction that survival alone could not accomplish, and still far removed from the biological complexity that had characterized the Permian Sea. The silence that followed the extinction was not the silence of an ocean at rest. It was the silence of an ocean in which the machinery of ecological function had been largely dismantled, and in which the slow, contingent, environmentally constrained process of rebuilding had only just and barely begun. Recovery, in the biological sense, is not a single process with a defined beginning and a clear endpoint. It is a succession of ecological reorganizations, each one building on the previous, each one contingent on the environmental conditions prevailing at the time, and each one constrained by the particular set of surviving lineages available to occupy the ecological roles that the extinction had vacated. The recovery of marine ecosystems following the Permian-Triassic extinction was, by every available measure, the most prolonged and ecologically complex recovery event in the Phanerozoic record. It unfolded across approximately 5 to 10 million years of the early and middle Triassic, and it did not simply reconstruct the Permian Ocean in a new form. It produced something fundamentally different, a marine world whose biological, architecture, dominant groups, and ecological dynamics bore only solid resemblance to the system that had been destroyed, and that would itself serve as the foundation for the extraordinary diversification of marine life that characterized the remainder of the Mesozoic era. The earliest phase of recovery, occurring within the first 1 to 2 million years of the Triassic, was characterized less by genuine ecological reconstruction than by the stabilization of the surviving biological community in conditions that, while still hostile, were no longer actively deteriorating at the rate experienced during the boundary crisis itself. Ocean temperatures, while remaining elevated above Permian background values, ceased their most acute phase of increase. Carbon isotope records, while continuing to show volatility, did not return to the most extreme negative values recorded at the boundary peak. The chemical environment of the ocean was not recovering in this interval, but it was no longer worsening at the rate that had driven the terminal phase of extinction, and this partial stabilization was sufficient to allow the surviving lineages to maintain their populations and, in some cases, to begin limited diversification. The ecological opportunities created by the extinction were, in principle, enormous. The elimination of 81 to 96% of marine species had vacated ecological roles across every trophic level and every habitat type in the ocean. Prey resources that had previously been controlled by diverse predator communities were now accessible to whatever predatory lineages had survived. Substrates that had been occupied by diverse benthic communities were now largely empty. Water column niches, previously partitioned among many competing species, were now available to the few lineages capable of exploiting them. In ecological theory, this kind of massive niche vacancy should drive rapid adaptive radiation, the accelerated diversification of surviving lineages as they expand into unoccupied ecological space. The Triassic recovery demonstrates that this theoretical expectation is only partially realized in practice, and that the rate and extent of adaptive radiation following mass extinction is strongly constrained by the environmental conditions prevailing during the recovery interval. The persistence of elevated ocean temperatures and continued chemical instability through the earliest Triassic imposed a physiological ceiling on recovery. Lineages that might, under more favorable conditions, have diversified rapidly into vacated ecological niches, were instead constrained to survival strategies emphasizing stress tolerance over ecological specialization. The evolutionary refinement of organisms for particular diets, habitats, or environmental conditions requires ecological stability across sufficient generations for natural selection to accumulate adaptive changes. In an ocean that continued to deliver episodic thermal and chemical stress, the selective premium on broad tolerance persisted, and the diversification that ecological opportunity would otherwise have promoted was delayed. The recovery of primary productivity, the photosynthetic foundation of the marine food web, was a prerequisite for the reconstruction of every trophic level above it, and evidence from carbon isotope records and the distribution of photosynthetic biomarkers in early Triassic sediments indicates that primary productivity remained suppressed and variable for an extended interval following the boundary. The phytoplankton communities that recovered earliest were dominated by opportunistic, small-celled forms capable of rapid population growth under variable conditions, the marine ecological equivalent of weedy species, rather than the diverse, structured planktonic communities of the Permian. This simplified primary producer community provided an inadequate and variable food supply for zooplankton and filter feeders, limiting the recovery of mid-trophic level consumers, and, through them, the predator communities that depended upon them. The return of reef ecosystems, when it eventually occurred across the Middle Triassic, approximately 4 to 6 million years after the extinction boundary, represents one of the clearest markers of genuine ecological recovery in the marine record. The organisms responsible for reef construction in the Triassic were not the same as those that had built Permian reefs. The rugous and tabulate corals that had dominated Paleozoic reef construction were gone. Their ecological role was eventually filled by scleractinian corals, a group whose origins remain somewhat debated, but which appear in the fossil record in the early Triassic and diversified through the Middle and Late Triassic to become the primary reef builders of the Mesozoic and, ultimately, the modern ocean. The emergence of scleractinian-dominated reef systems represents not a restoration of the Permian reef ecosystem, but the construction of a new one, different in its constituent organisms, its structural characteristics, and its ecological relationships, but functionally analogous in its role as a biodiversity hotspot and habitat provider for associated marine communities. The diversification of marine reptiles across the Triassic represents one of the most ecologically significant developments of the recovery interval, and one that fundamentally altered the architecture of the marine food web relative to its Permian configuration. Ichthyosaurs, highly streamlined, dolphin-convergent reptiles adapted for fast pursuit predation in open water, diversified rapidly through the early and middle Triassic, reaching large body sizes and occupying apex predator roles in the recovering ocean. Nothosaurs, plesiosaur precursors, and other marine reptile lineages expanded simultaneously, distributing reptilian predation across coastal, shelf, and open ocean environments. This reptilian diversification into marine apex predator roles was not simply the replacement of Permian predators by ecologically equivalent successors. It represented a reorganization of the predator guild, the set of organisms occupying top predator roles, around a fundamentally different physiological platform, with consequences for predator-prey dynamics, energy flow through the food web, and the structure of marine communities that persisted through the remainder of the Mesozoic. What the recovery of marine life following the Permian-Triassic extinction demonstrates, across the full arc of evidence now available from paleontological and geochemical investigation, is that biological systems possess a capacity for reconstruction that operates even in the aftermath of the most severe disruptions the planet has produced. That capacity is not unlimited, and it is not rapid, so human standards of time, the millions of years required for genuine ecological recovery following the Permian-Triassic extinction represent an interval longer than the entire existence of the genus Homo. But the ocean that emerged from the recovery interval was biologically complex, ecologically structured, and in many respects as productive and diverse as the one that had been destroyed. It was a different ocean, built from different organisms, organized around different ecological relationships, and, carrying within its biological architecture, the evolutionary legacy of having passed through the most severe filter the history of complex animal life had yet produced. The Permian-Triassic extinction does not exist only in the deep past. It exists in the present, preserved in rock, encoded in fossil chemistry, and reconstructible through scientific methods that have transformed what was once an inferential sketch of ancient catastrophe into an increasingly precise and quantitative grounded account of one of the most consequential events in the history of life on Earth. The evidence that makes this reconstruction possible is distributed across every continent, embedded in sedimentary sequences that were once seafloor, continental shelf, and coastal margin, and it has been accumulating in scientific literature for over a century, interpreted, reinterpreted, and progressively refined as analytical techniques have improved and the number of studied sections has grown. What scientists have assembled from this evidence is not a complete picture. It is, however, a coherent and increasingly detailed one, and the process by which it was assembled is itself a story about the capacity of systematic inquiry to recover knowledge from deep time. The boundary itself, the precise stratigraphic horizon marking the transition from Permian to Triassic, is identifiable in outcrop sections across the world by a characteristic combination of features that occur together at the same level. The disappearance of diverse Permian fossil assemblages, the appearance of geochemically distinct sediment layers, and the transition from bioturbated to laminated sediment textures collectively define a horizon that can be correlated across thousands of kilometers of separated outcrop. In many sections, this horizon is accompanied by a negative carbon isotope excursion, a measurable shift toward isotopically lighter carbon values in carbonate, minerals precipitated from seawater at the boundary, that reflects the disruption of the global carbon cycle by volcanic outgassing, biological productivity collapse, and the release of isotopically light carbon from marine and terrestrial organic reservoirs. This isotopic signal, consistent across sections from multiple paleocontinental regions, was one of the first geochemical indicators to suggest that the Permian-Triassic boundary represented not merely a regional faunal turnover, but a global disruption of Earth's carbon cycle. Radiometric dating has been essential to establishing the temporal framework within which the extinction and its causes are understood. High-precision uranium lead dating of volcanic ash layers, zircon crystals erupted during volcanic events, and preserved within sedimentary sequences at and near the boundary, has allowed the timing of the extinction to be constrained with a precision that would have seemed impossible several decades ago. Current estimates place the main pulse of marine extinction within an interval of less than 60,000 years, and some analyses suggest the terminal collapse may have been even more rapid, potentially occurring within 10,000 to 30,000 years in some sections. The same dating techniques applied to volcanic rocks of the Siberian traps have established that the main phase of flood basalt eruption overlaps precisely with the extinction horizon, providing the strongest available temporal evidence for a causal connection between the two events. the Siberian traps themselves, now exposed across an area of approximately 2 million square kilometers in northern Russia, though originally covering a substantially larger area before erosion, have been the subject of extensive geochemical and volcanological investigation aimed at quantifying the volume and composition of gases released during their emplacement. The total volume of basaltic magma involved is estimated at between 1 and 4 million cubic kilometers, making the Siberian traps one of the largest known flood basalt provinces in Earth history. Critically, the magma intruded through thick sequences of coal, evaporite and carbonate sediments as it moved toward the surface, and the thermal interaction between magma and these carbon and sulfur-rich sedimentary rocks likely generated additional greenhouse gases and ozone, depleting halogens beyond those produced by simple volcanic degassing. A process documented through the identification of contact metamorphic minerals and thermogenic carbon compounds in Siberian traps-related sedimentary sequences, the use of organic biomarkers, molecular fossils of specific organisms preserved in ancient sediments, has opened analytical windows into the boundary ocean that conventional paleontology cannot provide. The identification of isoreneurethane and related compounds from green sulfur bacteria in boundary sediments was made possible by the development of gas chromatography mass spectrometry techniques capable of detecting and identifying specific organic molecules at concentrations of parts per billion in rock samples hundreds of millions of years old. These molecules survive in the geological record because they are incorporated into the mineral matrix of sediments during burial and diagenesis, protected from complete degradation by the same processes that destroy most organic material. Their presence in boundary sections from multiple basins constitutes some of the most direct evidence available for the oonic conditions, the sulfide-rich, anoxic water ascending into the photic zone. That theory predicted, but that required molecular-level analytical tools to confirm. The lessons coded in the Permian-Triassic boundary record carry relevance that extends beyond historical geology. The fundamental processes driving the boundary crisis, greenhouse gas forced warming, ocean deoxygenation, acidification, and the chemical consequences of stratified, poorly circulating ocean water, are processes whose modern analogues are measurable in the present ocean. Current rates of atmospheric carbon dioxide increase, while not yet approaching the total fossil fosks of Siberian traps over their full eruptive history, are occurring at rates that may exceed the geological average rate of carbon input during the boundary interval when considered on a per-century basis. Modern ocean deoxygenation, the expansion of oxygen minimum zones documented by oceanographic measurements over recent decades, is proceeding in the direction indicated by boundary proxy records, driven by warming-induced stratification and reduced solubility of oxygen in warmer surface water. Ocean acidification, measured directly in the contemporary ocean through pH monitoring, is following the chemical trajectory that carbonate proxy records suggest characterize the boundary interval, though from a different starting point and at a different absolute rate. The Permian-Triassic extinction does not serve as a direct predictive template for the present. The boundary conditions, the timescales, and the initial states of the ocean and atmosphere are different enough that direct numerical comparison is scientifically unjustified. What it provides instead is a mechanistic understanding of how ocean chemistry, atmospheric composition, and biological complexity interact under conditions of sustained environmental forcing. An understanding grounded in the most complete, natural experiment in Earth's capacity for environmental disruption that the geological record preserves. The ocean nearly killed everything once. It did so not through a single catastrophic event, but through the compounding of individually manageable stressors into a combination that the biological systems of the time had no capacity to withstand. The rocks that preserve this history are not merely archives of ancient catastrophe. They are, read carefully and interpreted with precision, among the most instructive documents the natural world has produced about the conditions under which complex life can persist and those under which it cannot. Namu.